Hello and welcome. Big data clusters make SQL Server your data hub for everything, whenever and also wherever you are, depending on, well, when you're actually watching this. If you have any questions during the session, you can either pop them in the chat during the session, or you can just ask at the end. I'm going to leave some time for that, and I'm also available after the session through other channels in case there's any questions popping up. With that, my name is Ben Weisman. I'm a BI consultant from Nuremberg, Germany. I've been working with SQL Server 6.5. I love everything data related, and I also love everything speaking related. And what I'm very passionate about is actually getting new speakers on stage. So if you or anybody you know wants to get into speaking and you don't know how, please reach out to me. I would love to help you get you started, make that first step. So having that said, we're here today for big data clusters. So there's a couple of things that we need to look at before we can actually get started. That is Hadoop, that is Spark, that is SQL Server on Linux, that is Python, that is Docker, that is Kubernetes, and actually a bunch of more technologies that just did not fit on this slide. Well, obviously we will not be deep diving into any of those today due to lack of time and due to lack of knowledge on my end. But it's interesting to see where the SQL world is moving. If I had told you a couple of years ago that I'm going to install SQL Server on Linux, you would have told me that's not possible because SQL Server only runs on Windows. And here we go. SQL Server Big Data Clusters only deploys in Linux-based containers through a technology called Kubernetes. So we will have Kubernetes, and we take a quick look at what that means in a couple of minutes. And we got it exclusively running on Linux. So if so far you've said, well, let's assume you're a DBA. If so far you've said, well, I don't care about SQL on Linux because all we do is run stuff on Windows. We don't have any Linux machines. I don't care about all these containers and everything. This is where the world is moving, and you should get into Kubernetes, you should get into Docker, you should get into SQL on Linux. If you need to understand and work with Spark or Hadoop or Python, that will depend on your role. And it is more one of the things where the SQL world and the non-SQL world are getting closer and closer together because data is so much more than just SQL. So what is a big data cluster actually? So what does it get me what I didn't get before? And it's basically three things. It's a feature set that comes with data virtualization, which basically means you get data into your SQL Server that does not actually sit in your SQL Server. And while that may sound a bit strange, I'm going to show you what that actually means. It gets you a managed SQL Server, a managed on-prem data lake, because Big Data Clusters is a product that you can easily install on-prem. It is actually part of SQL 2019. It is not part of any of the Azure offerings. So if you're going to deploy that to Azure, you can do that, of course, but you'll be managing it. It's not an Azure or cloud managed service. So that means you're getting Spark and SQL together. But you also get other scale-out capabilities, and that means it comes with its own file server, but it also comes with something called the data pool that we're going to take a look at, which allows it to take fact tables and spread them across multiple servers, so not just multiple partitions, but multiple SQL servers, which is super cool. And last but not least, it is an integrated AI and machine learning platform with all of that data growing together, especially big data. I mean, that's kind of the obvious step that you also enable people and your user and your developers and end users, analytical users, whoever, to actually access that data using machine learning models and all that stuff. Before we really get started, let's do a little primer on the foundations of scale. For those of you that are not aware of what Hadoop is, my friend Bug Woody describes Hadoop as a supermarket, and I think that is a great analogy. What happens at the supermarket if you're standing at the cash register waiting to check out and there's 4 people in line? Well, ideally what the supermarket will do is they will open a second cash register, meaning there's not 4 people waiting in front of you, but only 2. Well, that's basically what Hadoop does. Just instead of selling you salads or whatever, what Hadoop will do, it will serve files to you. So the idea being you have one big flat file, 50 gigabytes, a terabyte, whatever in size. If you chunk that up into smaller pieces and spread it across multiple computers, servers, nodes, VMs, whatever you want to call them, and have them process these little chunks individually, well, it should be faster because reading through 25 gigabytes should be about twice as fast than reading through 50 gigabytes, and so on and so on. And that's basically what Hadoop does. And then we have Spark, which is basically nothing else but Hadoop in memory. So what you need to know for today is that Spark is a supermarket in memory. which is probably a bit confusing, but it will do for today. The other thing that we need to look at is that whole Kubernetes and containerization thing that I was mentioning. That is something that you've seen all before and that you've worked probably all before with for years or even decades, virtualization. Because at some point we realized, well, it's probably not the best idea for every single server to actually get bare metal and put it in a shelf, because CPUs get faster, memory get faster. There was no point in doing that anymore. So we came up with virtualization, basically running multiple computers on one physical computer, which is great because it saves resources, it saves space, it saves energy, but it still comes with a lot of redundancy, because if you're running, let's say, 3 Windows servers all running SQL Server on the same physical computer, on the same hypervisor, that means you will have 3 disks all carrying the Windows operating system, 3 disks all carrying SQL Server. So you're wasting 3 times the space, but also Microsoft now comes up with a new update for Windows, for SQL Server, for both. You will need to patch and maintain all these 3 machines. And this is where containers kick in. So containers basically abstract the operating system. They kind of share the operating system with the host. And they work with so-called images. So they share as much as possible. That means if we are running SQL Server in a container, no matter if we're running 1 instance of SQL Server, 2 instances, or 10, they will all be spun off from the same base image. So the only thing that we're, well, quote unquote, wasting here is memory. Because on the disk, it's 1 single image that we're just spinning up 1 time, 2 times, 3 times, however many times. And if we're updating this to a newer version, it's also the same file that we're updating. So we're not wasting disk space and we're not wasting maintenance time here. That's the great thing about containers. The bad thing about containers is they don't work so well together, and that is where containerization kicks in with the orchestration. And one of the things that you may have heard about is a thing called Kubernetes, which has been around for a while. It was initially developed and invented by Google as a project called named Borg. And now it is around, and by the way, Kubernetes is only one way to orchestrate containers, but it is probably by far the most popular, just as Docker is probably the most popular container technology out there at this point. The idea of Kubernetes is first you build a cluster out of so-called nodes, and the node can be a VM or a physical machine, depending on if this is a dev environment or if this is a high-performance prod environment, whatever we're looking at here, and basically form a base layer. Make this one, well, virtual machine is kind of the wrong word, but in the end, you're clustering hardware together, physical or virtual. And then on top of these nodes, you're running so-called pods, and a pod is nothing else but a collation of different containers that are working together, that are bringing stuff together, that belongs together, that serve a certain purpose, that serve a certain role. And the cluster orchestration manager, which is part of Kubernetes, this will make sure that the required amount of containers and pods is up and running at any given time on any given node where it can be run. So one of these nodes goes down, the cluster orchestration manager will immediately make sure that as long as there is another node that is available and fit for this, all the nodes and all the pods and containers from that specific node will be moved over to another node and spun up there again. And to make sure we're not losing any data, typically you will have some kind of external storage connected to your Kubernetes cluster, making sure that all these pods and all these containers will have access to the same data. So you as the end user, you wouldn't even notice in a usual case that one container just moved from one node to another, which is also one of the reasons why most of these container systems are running on Linux, because Linux is so much more lightweight. It's so much easier to spin that up, even though there are Windows containers out there. And the nice thing about that is it means we can actually scale by a purpose. I need a little more of this specific functionality instead of just coming up with a huge new server that basically gets me 100% of everything, but I'm only using 10%. Well, I need that many web servers. I need that many business logic servers. I need that many data tiers. It's not even, service is not even the right word, but this is just the amount of instances that you spin up for that. And depending on your workloads, this may even vary during the day or during the week or during the year. You just spin up more or less of these specific pods and containers. So much for these containers for now. If you want to learn more about that, there is one book I can highly recommend, which is the Illustrated Children's Guide to Kubernetes. It is, as the name suggests, a children's book. That giraffe that you see there, Piffy, she will guide you through the world of Kubernetes and explain all these concepts to you very well. It is an open source book, because usually that would be the point in time where I start handing out books. Well, since I'm sitting here at my office and you're sitting either at home or at your office or wherever you may be sitting watching this, hopefully some nice place, the only thing I can offer you is to download it for free, because it is an open source book. Or the other thing, if that book leaves any questions unanswered, talk to this guy, Anthony Nocentino. He's also got a ton of courses out there on Pluralsight, for example. He's got great blog posts on the topic, so he knows everything you need to know about Kubernetes. So, enough of primers and all these abstract things. Let's talk about big data clusters. And let's talk about the architecture and the, core concepts of a big data cluster first, I would say. This is the only part that you would even get without a big data cluster just in a regular SQL Server 2019. And this is the data virtualization part. Because data virtualization in SQL Server 2019 and big data clusters are essentially SQL Server 2019, just with a little more components, works through something called Polybase, which you may have heard before and which you even may have worked with before. And that is the only part of that feature set, again, that you would get not just from a big data cluster, but also from a standalone or any kind of SQL Server 2019 installation if you enable that feature. So let's take a quicker look at what that actually means. So what Microsoft did in SQL Server 2016, they introduced Polybase, and with Polybase came the concept of external tables and external data sources. And the idea was, and that was also the backbone, if you want so, of parallel data warehouse. The idea was to bring in data that sits in files without necessarily loading it into SQL Server. So the idea of an external table is you create a construct that looks like a table, but it's actually accessing data that sits somewhere else. That's why it's called external. It still follows the idea of a table, so it will have SQL data types and stuff. It will just point to somewhere else. And in 2016 and 2017, those were external files, basically. Well, what happened in 2019 is that Microsoft tremendously increased the number of data sources that you can access. So we can now access data that sits in Teradata and another SQL Server in Oracle. NoSQL data like MongoDB. We can access data that sits in Hortonworks. We can access data using generic ODBC drivers. Like we could bring in data from a SharePoint list, for example. All that through Polybase, and all that in any SQL Server 2019 installation if we want so. Which may remind you of a linked server, but think about the way a linked server works. First of all, how is the query built? If you're querying a linked server, you would have select star from linked server name, .database name, .schema name, .table name. What happens if the server name changes? Well, all your queries break. A query against an external table, a query against Polybase looks like select star from schema.table, which means if your target server name changes, all your changes are pointed in the background at one single central piece instead of upgrading and breaking all your queries. The other thing about Polybase queries is that they are scale-out capable, whereas a linked server query is always single-threaded. There's a couple of more differences that I'm not going to dive into, but it might even just be worth it if you're heavily using linked server to just evaluate if switching that to Polybase might be a good option for you. So far, so good. Like I said, that is the only part that you would get with any SQL Server 2019 installation. All you're going to see from now will require big data cluster, and it will require this to run on a Kubernetes cluster. I'm going to separate that out into two little parts. You see the control part on the left side, and we're going to basically ignore all that for today. There is just not enough time. But there's just a bunch of containers and functionality in there, like a container making sure that you got Kerberos working, a container making sure that you got a web service interface to actually look into the status of your big data cluster, and we're actually going to see that web interface. We're just not going to look into the container. Just a bunch of shared services, and also the big data cluster controller that will make sure that everything that you will see to the right is actually working and working together and communicating well. But the actual action, the interesting part, is happening here on the right side where it says BDC. So that's what we're going to look at. I kind of went over that in the beginning, the first thing you see here is the SQL Server Master, and the SQL Server Master is your main entry point into your big data cluster. And the SQL Server Master is just a regular SQL Server 2019 with the only difference potentially that it is running on Linux, and your regular SQL Server at this point may not be running on Linux. So, what that SQL Server Master does for you, it communicates with all the different so-called pools in your big data cluster. And the first pool we're getting to know here is the compute pool. The compute pool is probably the most abstract of all the pools that we're going to see, because there is basically no interaction directly with it at all. It is just there and doing its magic. You see one SQL Server in my compute pool. That is something I decided at the time of deployment, and I could have also decided to have not one SQL Server instance there, but 2, 3, 4, any number of SQL servers. And the idea now being, when I'm querying my SQL Server Master against data that is sitting in an external data source, like coming from another SQL Server through Polybase, the SQL Server Master can now, instead of querying that external source directly and having all that workload on its own, run that through the compute pool. I'm running a query, and that query is combining data from 4 different external data sources. I have 4 instances in my compute pool. Well, potentially, these 4 instances might all be working on one of these queries each. Again, just increasing my query performance. Now we're getting to one of the first less abstract pools, the data pool. And what you will probably immediately notice is that my data pool has 2 SQL servers in it, because that is the lowest number of instances that makes sense in your data pool. The idea of the data pool is you take data that sits in a bigger table usually and push it to the data pool, and through round robin just push it to 2 different instances. So you have a fact table, 100 million rows. Those 100 million rows end up on 2 different SQL Server instances in your data pool with 50 million rows each. There's one thing to be aware of: the data pool does not support transactions, so don't think about making this your primary storage for anything. Just think about it as being a cache. But from the end user perspective, again, I would say select star from my big fact table, and all the magic will happen in the background, where all the data coming from both instances in my data pool, or 3 instances, 4 instances, 8 instances, will kind of be union all together. But all that happens automatically in the background. I don't have to worry about that. So while I could have built something like that manual with lots of union alls and linked servers and I don't know, whatever black magic would need to be involved to get that working, this is now happening all automatically. So what I will just do is I will create an external table on my SQL Server Master, and this will automatically make sure to create the corresponding database and table and even a clustered column store index on each of these tables in my data pool. The next pool we're looking at is the storage pool. And this is where it gets even more exciting potentially, because the storage pool, it brings together SQL Server and Spark. So it has Spark nodes and SQL Server nodes. So that also means you can speak Spark and T-SQL directly on that. It comes with its own HDFS, so when you're deploying your big data cluster, it deploys its own distributed file system. I mean, how cool is that? No need to worry about that anymore. If you already have an HDFS, like an Azure Data Lake Store or something like that, that's cool. You can bring it in through so-called tiering. You just mount that data into your into your big data cluster HDFS. And again, the number of SQL Server nodes, the number of Spark nodes in there, that's something you decide at the time of deployment, and it is completely up to you, and it will depend on your workload. So if you're doing lots of stuff in Spark, you may end up with 8 Spark nodes in here. Or if you say, well, I'm not using Spark at all, we're just using this to basically read files and get them right into SQL Server, well, you may have 8 SQL Server nodes in there and just 1 single Spark node. That is, again, depending on your requirements and your workloads. And the last pool in here, getting a little more abstract again, is the application pool. The application pool does everything and nothing. It comes with a machine learning server. You can run integration services packages there. You can deploy web applications in there. All kinds of things, but it's stuff that you need to deploy to it. It doesn't do much out of the box. I mean, you could argue that SQL Server itself doesn't do much out of the box, but the application pool, it has endless possibilities, but you actually need to code something for that to make sense. So we will ignore the application pool for today and mainly focus in our demos on the master instance, the data pool, and the storage pool. And that also means the application pool is the only exception to the rule that you usually talk to the SQL Server master, because of course, if you're deploying a web application, you want users to communicate with that application and not go through some kind of detours. Still, for all of the other pools, your endpoint will, except for maybe management purposes, always be your SQL Server master. So this is the only endpoint you connect to, no matter if you're speaking Spark or if you're speaking T-SQL, no matter if you're getting data from the master instance or from the data pool, no matter if you're getting data from the data pool or from the storage pool. All that will happen for your SQL Server master, which is super cool, because that also means your end user, they don't have to worry about that. And even if over the life cycle of your data may be shifting from coming from a virtual table, moving into master instance, moving into the storage pool, moving into the data pool, or in whichever order, they don't need to worry about that, because all they do is run a query on your SQL Server master instance and it will just run from there. So, time for a demo, time to see big data clusters in action. So, what you will notice here is I'm in Azure Data Studio. For those of you who are not using Azure Data Studio yet, please start using Azure Data Studio today. And if you say, well, I can't use Azure Data Studio because all of the stuff that I'm doing is on-prem, you can still use Azure Data Studio, because Azure Data Studio is not just for Azure workloads, despite the name potentially suggesting otherwise. So if you're taking nothing away from today but this, please start using Azure Data Studio, please, please. It has so many cool features. It starts with the fact that it has a dark mode, which usually sells a couple of you, but also it runs natively on a Mac and Linux, which is obviously super helpful for an application that you're deploying to Linux. It comes with a bunch of extensions, and it also comes with a bunch of wizards that we can use for especially big data clusters. It also comes with a looking glass directly into our file server, more on that in a bit. But what I can do here in Azure Data Studio is I can run a wizard, which is called the Data Virtualization Wizard. And what that wizard is doing, it comes with one of these extensions. And it is not in Management Studio. And by the way, Azure Data Studio is not taking your Management Studio away, it's just complementing it very well. It's asking me, where's the data coming from that you want to virtualize? SQL Server, Oracle, MongoDB, Teradata. All the other sources that I've mentioned, they do not come with a wizard. You would have to come up with a T-SQL yourself, except for CSVs, and we're going to take a look at CSVs in a bit. So what we will just do is bring in data from another SQL Server, and for that purpose what I did is I have actually just created an AdventureWorks LT database in an Azure SQL database. The first thing the wizard is asking me is let's try this again. There we go. For a master key, because this is a brand new database, we will be working and storing credentials and passwords and everything in here. So, well, SQL Server is like, yeah, it might make sense to encrypt that. What we need next is a name for our external data source, which is just a pointer, the server name of that SQL Server, a name for our credential as well, again just a pointer, and username and password. What we can do with that is, or what the wizard will now do is it will connect to that data source and get me a list of all the tables and all the views in there. Let's say we want customer and customer address. If I click this, as you can see, the only thing I can change here is what is my target schema, what is my target table name. I will change my schema to DBO on actually both of them. I cannot change any data types, I cannot change if it's nullable, I cannot change any collations. What I could do is make this a W underscore a customer address, or virt underscore customer address, or anything like that. If I want to have some naming convention there, that's the only thing you can actually change here, schema and table name. All the rest will be inherited as it is because it's an external table, it's not an external view. If I want to make my integers big ints or something like that, I would need to do that in my query. This cannot happen on the fly in the middle. This gives me a little overview of what's going to happen. So we will create a master key, a credential, an external data source, and also these two external tables. And I will just generate a script out of that. And what you see in that script right here is it looks just like a create table statement, but it says create external table, and instead of on primary or something like that, what we will see is it comes with a location pointer, and that location pointer is looking at a data source, which is my BWAW, and it's looking at a table in my AdventureWorks database. And if I connect to my BDC here and run that query, I can now run this notebook, and this notebook will do a select top 1 staff from customer and a select top 10 from customer and a join customer address, and it will get back my results. It looks like a regular query against regular SQL Server tables, but the data that I'm consuming here is actually coming live and in real time from my Azure SQL database. Every single time I hit that little play button here, that data is coming live from Azure, which is great if I want this data to be real time, which is horrible if I consider, oh, well, there might be latency, there might be network outages, and there might be completely different workloads happening on that source system. Maybe the least of our concerns in the AdventureWorks database, obviously, but that's always something to keep in mind. So when working with data virtualization, use it wisely. It might be a great replacement for your linked servers. It is not a great replacement for all your ETL routes, because this might mean that potentially you have 50 analytical users and they are all hitting your OLTP system with live queries and stuff, and in a way that your OLTP system is just not made for. So do not make a virtual data warehouse out of that. Apart of the fact they would be losing out on stuff like slowly changing dimensions and everything if you're not actually loading and staging that data. But use it for those cases where real time makes sense for you from a source and target perspective. So much on data virtualization. Let's get to the storage pool. To work with the storage pool, we need data to sit in our storage pool. And what I did in advance is I've uploaded a couple of CSV files here for us. Airlines, airports, flights. This is just a public data set coming from Kaggle, where you can use flight delays from, I think it's 2006. So what we will do here is first we'll change our database context. Next thing we need is we need a pointer to the storage pool. Anything around Polybase, anything around big data clusters is in the context and the scope of a database. So since this is a new database that I've just created this morning, I need to just create this pointer, and all this does is it creates a data source that says, well, by the way, you're in a BDC and this is where you would find the controller endpoint for the storage pool. What I can do now is I can take one of these CSV files like airlines.csv, right mouse click and say virtualize data from CSV files, which is coming from that very same wizard that I was using earlier when I was bringing in data from another SQL server, which will ask me, well, in which database do you want to do this? What's the name of your, or the target name of your new virtual table? What's the name of your file format? I'm just going to name that CSV. Click next. What it will do is it will give me a preview of what's in there. If we look at the first 50 rows, since this file actually only has 14 rows, well, it gives me the full file. Hit next again. What we see here is it's suggesting nothing less than an nvarchar 50, where I could say, well, but this is an airline code. The airline code will never have Unicode characters. The airline code will never be larger than 2 characters. Why isn't this a char 2? Well, that's what the wizard does, and with only 14 rows, the memory overhead is probably slim enough that we don't need to worry about that still. I could go ahead here and say, well, let's just make this a char 2. The only thing that you need to consider, this data type needs to match what is in your file. I could even make this an integer at this point. I just couldn't query it afterwards because that would get me a type conversion error. Next, gives me an overview again, generate script, and it looks very similar to what we've seen before. Create external table, these are my 2 columns, with the exception that this time it's pointing at a file, not at another table, and also adds the file format. We did not need the file format when getting data from SQL because SQL has its own schema, a CSV file does not, so we need to provide that to it here. We can point it either to a file or we can point it to a directory. If we point it to a directory, the only prerequisite for that would be that all the files in that directory actually share the same format. So you have a web server that spits out weekly, hourly, daily, whatever period in time log files directly to your HDFS. Just spit them all to the same folder and you can work with them without needing to create an external table for every single file. In this case, I have 3 completely different files, so I'm pointing it right at the file. So whatever your use case requires, you can do that here. Let's just run that real quick. And now I can do select staff from airlines, just like I did select staff from customers. And look at that, I'm getting that back just as if it were a regular SQL table. Interesting, because, I mean, look at that. I'm just querying a CSV file, as if it were a SQL Server table. I don't even have to go through the wizard. If I already know my structure, know where everything is, and know how my T-SQL needs to look like, I can just run this, because all of this is just controlled through T-SQL, and do select top 5 from airports. I just added another file that sits right here in my HDFS, and I'm just querying that. And I could now go ahead and join them and so on. One thing that we need to consider is, when files get bigger though, CSVs are not the greatest of file formats. So let me show you something here real quick. I'm just creating another external table pointing to a directory in this case, again with CSVs, but this directory only has one file actually, so it doesn't even make that big of a difference. That query took 5 seconds. Now I'm creating another external format called Parquet file, which is, well, basically creating the format for Parquet files. Think of Parquet as clustered column store for flat files. So it basically encrypts and structures my CSV file. We create another external table pointing to a Parquet file with the exact same content. Whoa, 5 seconds, 1 second. So 5 times as fast for the exact same result. That is just something to keep in mind. Convert your files to Parquet. You will probably get speed improvements of 5x, 10x, I've seen up to 100x by just converting files into Parquet, and that is something that big data clusters, due to the built-in Python and due to the built-in Spark, can do out of the box. How does it look for a real-life scenario? Let me just close some of that stuff here, so we get a little more space. Well, one of the reasons why we're not all in the same room together is a thing called COVID. So that's why I came up with a demo data set around COVID-19. Well, I did not come up with the data set. I'm getting that data set from, or actually multiple data sets from GitHub, because GitHub has lots of great data sets that we can use, and we can use them for free and consume them easily. So first I would need to run, I actually already did that, this preparation script. And what that preparation script will do is it'll create a database name called COVID. It will create 4 schemas, 1 MI for my master instance, 1 for my data pool, and 2 on my storage pool for Parquet and CSV files. There is no need to separate them out into different schemas, but it helps obviously when reading the queries later to just understand where the data is coming from. I'm creating the pointer to my storage pool again. I'm creating my CSV file definition, my Parquet file definition again. I'm creating 1 external table that gives me the population per country, pointing to a CSV that doesn't even exist yet. I'm creating 3 tables on my storage pool with the recovered, confirmed, and deaths cases. Again, don't exist yet, but we will get there because we will get those from GitHub. Pointed to the data pool. Then we create a table on the data pool that will have my COVID development, and that's again the interesting part. That data source will be the data pool with a distribution of round robin. And the difference on the data pool compared to the other sources is the data here doesn't exist yet, but it will now be even more the table structure, I should say, doesn't exist yet. It will be created by SQL Server. By running that query, what SQL Server will do is it will connect to every single node in my data pool, to every single SQL Server instance in there. Create a database in there called COVID, because that's the name of the database I'm in right now, if it doesn't exist yet. In that database, create a table called COVID development with exactly that structure. In that database as well, create a cluster column store index on each of them. And by saying distribution is round robin, when I'm inserting data into that table, one record will go left, one record will go right, left, right, left. It doesn't actually do it record by record, and we're going to see that. So it does that in chunks, so you will have a almost round-robin evenly distribution, but not 100%. And since my countries coming from my COVID dataset and the countries coming from my population dataset are almost but not always the same, I'm also creating a mapping table on my master instance where I'm just mapping them together, and in the end just a little view on where I'm consuming some of these tables together and querying them. All of that is on GitHub, and I'm going to get you the link at the end of the session. So if you want to try out that demo, you will just run that whole notebook and it will get you up and running. So the first thing we need to do is we need to get the data on the population, and that data, it's just showing here the first 5 rows, is actually coming from GitHub. I've left the link here in the notebook. So if you just go there, there's an open data set on GitHub that will just have the population per country per year. The last year it has is actually 2018 for every country, but that is good enough because that number is not so volatile. And what that will do is it will just take that number, it will take my population and save it as a CSV file right here on my storage pool. And we'll save it, since I went through Spark, it will save it into 2 files because I got 2 nodes running in the background, so it will immediately recognize that, split it in these 2, so my Spark and my HDFS can actually work on that in parallel. So I could also preview that. I would see, oh, okay, this is by country, and it doesn't even just have countries, it also groups them into some kind of all kinds of regions actually. But if I scroll down a bit, you see, okay, so we got Angola here, and that's the number, and Andorra, and that's the number of inhabitants, and so on and so on. We can just take that later and consume it in our queries. And since that file is rather short, I just leave that as a CSV. There is no point in converting it to a Parquet file. Next part is we need to get the COVID cases. And the COVID cases, that's a bit more interesting because I'm getting them from the Johns Hopkins University, also from GitHub. And what they do is they provide them in 3 different files, 1 per recovered, 1 per deaths, 1 per confirmed, which also matches the external tables that I've created in my preparation script. The issue with what they're doing is they just add a column every single day. So every single day you will see a new column coming up with the numbers for that day. While that may be easy for them, it's harder to consume for us. So what we're doing instead is I'm using a built-in Python function called melt. For those of you that are primarily T-SQL developers, melt really blew my mind how easy that is, because it's basically a dynamic unpivot. What it will do is it will just take all these columns and merge them into rows, which is what we see down here. So I will just end up with province, country, date, and the number of recovered, the number of deaths, the number of confirmed cases, and they can that now I got this in the format that I can actually work with, because what I can do now is I can say, you know what, let's just take a look at that data first. Give me the first 10 rows from my recovered number. Okay, so this is per province, this is per country, but we actually wanted to see some development. So I want this per day, and I want to have 1 line per day that will have recovered and deaths and confirmed per country and day all grouped up. So I'm pushing that to my data pool. So on my dp datapool.covid development, I'm just inserting that data from that query. Look at that. This is a regular SQL query. So I'm just doing truncate and insert and select as if it were a regular table, but in the background, all that data has been spread out. I can do a select count star on that and say, okay, that's around 40,000 rows. And by the way, for 40,000 rows, you would usually not go through the trouble of using the data pool. Still, if I look at that using the add data source SQL data pool hint, what I can see is what that hint will do is it will just run that query on every single node in my data pool. And like I said, there's 2 of them in my deployment here. So I end up with 20,000 rows here, 20,000 rows there. Gets me my same number as here, just so I can see, well, they're pretty much evenly distributed. Where I can now say, hey, okay, I only want the active cases, which is basically a combination of new cases minus death minus recovered per day. And I only care about Germany right now. So I'm doing a select date and active from my development where country is Germany and order that by date. And since I'm in Azure Data Studio, I can even make this a fancy chart which might make it easier to consume. So, okay, this was the first wave, and it looks like we're very much approaching a second wave steeply right there. Then I got my population data, which we also saw in the preview. And what I can do now is I can even bring those together, just like a regular SQL query again, where I can say, well, for the last day that we have, give me the countries with the most infections, with the most active cases per million. Getting data from my data pool, joined against my mapping table, joins against my CSV. So I'm querying a regular SQL Server table against a CSV file, against technically two physical tables on two completely different SQL servers, but in my query it all looks like this is a regular SQL table just against three tables. Pretty cool stuff. Still, if I say, well, I don't care so much about T-SQL, I work with Python, I work with R and all these other fancy languages out there, well, you can do that, accessing the very same data. So let's take the very same data set, let's even take the very same query and matplot that or whatever you want to use, and you can use that to visualize the data, you can use that to work with the data, to wrangle with the data. It's still coming from the very same data source. So your data scientists, your machine learning experts, all of them, they will be using the same data in the background, which is one of the glorious things that I love so much about big data clusters. So, how can we manage all that? Well, there's, as you have seen by now, a bunch of components in a big data cluster. So how can we make it manageable? How can we make this easy? Well, there's a couple of tools and a couple of them will be probably new to you. First of all, we need to make sure that our Kubernetes cluster is up and running, which is right here on the very left. Then we got the BDC part itself. And then we got the, well, what I call the monitoring part. So we got kubectl, which is the tool that we're using to actually control the Kubernetes cluster. We got AZData, which is a tool that is not just for big data clusters, but you will use it every single time you upgrade or you deploy a big data cluster. So it's a command line tool that runs on a Mac, that runs on Linux, that runs on Windows, and you could use it to create a new big data cluster on an existing Kubernetes cluster. You can use Azure Data Studio to not just look into your big data cluster, to do not just work with the data, but also to manage your big data cluster, and we're going to see that in a sec. And then there's two web interfaces, the Grafana interface and the Kibana interface. These are two open source tools, and these two open source tools basically are your looking glass into your big data cluster. So the Grafana interface collects all your metrics like SQL metrics, host metrics, what's my CPU like, what's my weight stats like, and all that. And the Kibana interface basically, through Elasticsearch, collects all the log files from all the containers. Because keep in mind, you got so many pods, you got so many containers and so much stuff there. If something goes wrong, if you would need to connect into every single one of these containers and check out what their CPU usage, what their disk usage, everything is like, this might take forever. Whereas if you just use that centralized interface, that is much easier to achieve. So let's take a quick look at that as well. So this comes with the ability as well to manage my big data cluster, and this also comes with the link into this Grafana and Kibana dashboard. So let's just authenticate against that. And in the Grafana dashboard, like I said, this will give me all the different metrics, like what are my weight stats on my different nodes, so I could see what's my different data pools doing, what's my storage pool doing, what is my master instance doing, but also what is my host node doing, like how long has this been up, what's my CPU usage, what's my RAM usage. These interfaces, they are your looking glass into your big data cluster. And within Azure Data Studio, this would also come with a link to all the other endpoints that your big data cluster would have. So if you would need to connect to any of these nodes or roles specifically, you could do that. And it will also come with a couple of other mechanisms and notebooks to troubleshoot your big data cluster, and you could also deploy your big data cluster right out of Azure Data Studio. And with that, are there any questions? I will be here in the chat to answer them. I'm also available after that. My contact details are up here again. You can reach me on Twitter, you can reach me by email, you can reach me on LinkedIn, whichever works best for you. I've also included 3 links for you. I wrote a book with my friend Enrico on big data clusters, which you will find at bookmark.ws/bdcbook. I made a course on Pluralsight where I'm also going more into the specifics on how to deploy a big data cluster. So if you want to get into a big data cluster deployment, that might be interesting for you. And all the code that you've seen today will be on my GitHub. So if you go to bookmark.ws/bdccode, you will see this code and also a couple of other sample notebooks getting data from different data sources and exposing them as external tables for your big data cluster. Again, if there's questions, please feel free to ask them now or reach out to me afterwards. And with that, thank you so much for your attention. Have a great rest of that conference, and I hope to see you all in person again soon.